Okay, so in part 3, we are going to continue talking about probability, talking about compound events. But this time we're going to be talking about two ideas. We're going to be talking about complements and the probability of at least one, and also we're going to be talking about conditional probability. So first off, complements and the probability of at least one. So when we're finding the probability of some event that is occurring at least once, we should understand that a couple of things logically follow. So at least one is the same as saying one or more, right? And the complement of getting at least one of an event is that you get none of that event. So we can use the complementary probability law in order to get our answer in these cases. Okay? So for example, a family has 10 children. Let's just assume that, there's only girls and boys in the world. Okay? What is the probability of getting at least one girl? And what about not getting at least one girl? So we have to understand the internal logic that not getting at least one girl in 10 births is the same as getting no girls, which is also the same as getting 10 boys. And also not getting at least one girl in 10 births is equal to getting no girls, which is equal to getting 10 boys. Okay? So when we are trying to get the probability of getting at least one event, we can let A being the getting at least one of some event. The complement of A is getting none of that event. And so the probability of getting none of the event, right? Probability of the complement is the probability that A does not occur. And this is really easy to figure out based on the multiplication rule. All we have to do is subtract whatever we have from 1. And so the probability of at least one occurrence of event A is the same as 1 minus the probability of no occurrences of A. So let's look at an example. So in your textbook, in one of the exercises, there's a table of blood groups and RH types of random subjects. Okay? Now, let's say that the probability of randomly selecting somebody with group AB blood, okay? Blood types can be either O, A, B, or AB. So in this study, the probability of randomly selecting somebody with group AB blood is 0.0526. Now, let's say a researcher needs at least one subject who has AB blood. If we pick 20 subjects randomly, we want to find the probability of getting at least one subject with group AB blood. So is the probability high enough in just a sample size of 20 that the researcher can be reasonably sure that they'll get at least one person with AB blood? Okay. And so remember, getting at least one person with AB blood is A. The complement of that is getting no one with AB blood in those 20 samples, those 20 people. And so the probability of getting no one is the same as, so the probability of getting at least one is the same as 1 minus the probability of getting no one with AB blood. Okay. So let's let A be the probability of, let's let A be getting at least 1 out of 20 subjects with group AB blood. Okay. So we have to identify the complement. The complement is not getting at least one subject with AB blood among the 20 that we pick, okay? Which is the same as saying all 20 subjects have a blood type other than group AB. So next, what we do is find the probability of the complement. So if there's 0.0526 probability of a person having AB blood, okay, then 1 minus 0.526, which is 0.9474, is the probability of a person not having group AB blood. Okay? So that's the complement. If the chance of having one person is 0.0527, the chance of having no one is 1 minus 0.0526, which is 0.9474. So now we want, that's the chance of having no one have AB blood. So if we want to know, we pick 20 people, right? What are the chances that no one has AB blood out of 20 people that we picked? Well, we just have to multiply our probability of no one getting, one selected, no one getting, and we do that 20 times. Okay, because we're picking them 20 times. So 0.9474 was the probability of you pick one person and they don't have AB blood. If you're picking 20 people, you're going to multiply 0.9474 multiplied by itself 20 times. So 0.9474 to the 20th power is equal to 0.339. Okay. That's the likelihood of picking 20 people and no one has AB blood. So the last step is, now that we know the complement, the probability of the complement, we find the probability that we will get one. And that's equal to 1 minus the probability of the complement. So the probability of getting 1 out of 20 is equal to 1 minus the complement of that, getting 0 out of 20. So that's 1 minus 0.339. And that gives us 0.661. So for a group of 20 subjects, there's a probability of 0.661 of getting at least one person with a group AB blood. So this probability is not super high, right? So the researcher, if they want to be reasonably sure that they're going to get somebody with AB blood, they might need to pick more than 20 people. Okay. And when you pick more than 20 people, basically you're multiplying this 0.947 times itself more times. And so you're making that number smaller and smaller. So the likelihood of getting no one is getting smaller and smaller. So the likelihood of getting someone gets bigger and bigger. Okay. So the last topic we're going to talk about is conditional probability. So sometimes the probability of an event is affected by knowledge of some other event that has occurred. And so probability of an event can be conditional on something that's already happened. So a conditional probability is a probability that's obtained with additional information of some other event that's already occurred. For example, if we want to know the probability of a golfer making a hole in one, right? Random golfer, it's going to be, based on past results, is it going to be 1 out of 12,000. But if you have the additional knowledge that the person that you select is a professional golfer, then that probability is going to change. And according to USA Today, professional golfers will get a hole in one, with a probability of 1 over 2,374, which is a bigger a number than 1 out of 12,000. Because they have certain skills, and so the probability of them getting a hole in one is a lot bigger. So conditional probability is the notation will be familiar to us because this is a kind of compound event, right? It's compounded with the probability is compounded with some condition. So the probability of B line A, it denotes conditional probability. And it means that event B is occurring given that A has already occurred. So the probability of B happening, B line A, can be found by dividing the probability of events A and B, both occurring, by the probability of A. So probability of B line A is equal to the probability of B and A happening divided by the probability of A. And so this conditional probability is really just a variation on our multiplication rule. If we remember what our multiplication rule, this was when we had the overlap. We wanted to know A and B occurring, right? So the probability of A and B occurring in the same trial when and then A and B happening in different trials, right? That's A and B. And the probability of B line A represents the probability of B occurring after A has already occurred. And our multiplication rule for that was probability of A and B is equal to the probability of A times the probability of B happening after A has already happened. That was our multiplication rule. So for our conditional probability, all we're doing is solving, in this equation, solving for probability of B line A, right? And that tells us it's probability of A and B over probability of A. So let's do an example. Let's practice. So let's go back to our 550 test subjects, job applicants, and their drug screening. So if one of the 550 test subjects were randomly selected, let's look for the probability that a subject had a positive test result given that they actually use drugs. So the starting condition is that they actually use drugs and they tested positive. So what we're looking for is the probability of a positive test result among people who actually use drugs. Okay? So subject uses drugs is our starting condition. So there's two approaches. We can do this formally, and then we can use what's called an intuitive approach. The formal approach, it's important to understand what goes into that, and then we can sort of use the intuitive approach because it's simpler. So remember that the probability of B line A is the probability of a positive test result among those already subjects that are using drugs. Okay? So the probability, that value is equal to the probability of A and B over the probability of just A. So probability of A and B, okay? A and B. This means that the probability of it's the probability of subjects that use drugs and have a positive test result multiplied by positive test result given that subject uses drugs over number of subjects who use drugs. Okay, so what we have here is 45. These are the subjects that use drugs over 555. So that's the total in the study, and then total people who use drugs was 45 plus 5. So that's 50 over 555. And that gives us 0.900. Now, we can also do this through an intuitive approach. Okay? What we want is the probability of the positive test result given that the subject uses drugs. Okay? Now, what we always want to think about is what is our starting condition, because that's our denominator. And since we're looking for positive test results given that subject uses drugs, our starting condition is subject uses drugs. That's our denominator. Okay? So the amount of individuals who use drugs, who actually use drugs, are this 45 plus 5. 45 that test positive and 5 that tested negative. So that is going to go, that's 50, and that goes in our denominator. So how many subjects actually use drugs? And what we want to know is, out of those subjects, what's the probability that somebody actually tests positive? So the only group that tests positive and uses drugs is 45. And so we can put that number in the numerator. That number in the numerator over 50 gives us our 0.900. It's the same value that we got with the formal approach. Okay. So when we look at this conditional probability, this is our starting condition. That is our denominator. And the other value is then going to be our numerator. And that gives us our conditional probability. Let's do another one. Now let's ask the question a little differently. So if one of the 550 test subjects were randomly selected, find the probability that the subject actually used drugs given that they tested positive. So we're flipping it around. So now this is, of the people who test positive, how many actually use drugs? Okay. So now our starting condition is those who test positive. So if we look at this table, the people who test positive are 45 plus 25. That's 70. And the people who actually use drugs out of those people who test positive is 45. And 45 over 70 is 0.643. Okay. So that is very interesting, because basically we asked two questions. We asked, number one, what is the likelihood among the people who use drugs? What's the probability that they will test positive? That gives us 0.9. If you use drugs, there is a likelihood of 0.9 that you will test positive. But if we ask the different question, of those who test positive, how many actually use drugs? That's a different number, because there are more people who test positive than actually use drugs. That's 70. So 45 of those 70 actually use drugs. And so the likelihood of actually using drugs when you already test positive is only 0.643. Okay. So that's very, very interesting. And it also highlights something. It highlights something called confusion of the inverse. You notice that the probability of among the people who are using drugs who test positive, that probability was not equal to the inverse. That of the people who test positive, how many actually use drugs? So that example really demonstrates that in general, the probability of B happening when A's already happened does not equal the probability of A happening assuming B already happened. Okay. Now there could be individual cases where those two are the same, but in general they will not be equal. And if you incorrectly think that they are equal, then you are displaying something called confusion of the inverse. Okay. That you don't understand that when you have two conditions, the starting condition can really determine the probability, and it can make, you have two conditions. If you swap the starting condition, it doesn't necessarily mean that the probability is going to be the same.